Okay, so in class today, we were talking about Riemann sums, and we were talking about this limit as n approaches infinity of the sum of our areas of our rectangles, and we said that that relates to our integral. So we're going to use this idea to help us determine the exact area under the curve of our x squared function from 0 to 5, or the integral starting at the x value 0, ending at the x value 5 of this x squared dx. So we kind of talked a little bit about these formulas at the end of class today. And we're first going to talk about some initial information that we're going to need in order to solve or in order to actually calculate this exact area. So we'd kind of said that at the end of class, we weren't sure exactly how many n's there were because we said that that n was approaching infinity. So it's going to be a lot. So we're going to leave n as an unknown right now. We do know that delta x is our b minus a divided by n. So we know that our b minus a would be 5 minus 0. And if we don't know n, we're just going to leave that as n for right at the moment. So our delta x is going to stay as 5 over n. And then we need to know about this x sub I, because we know that that's kind of a part of our formula up here, or an element of our formula. So we said that x sub I is a plus delta x times I. So our lower limit, or our starting x value here in this particular function, is 0. Our delta x we just calculated to be 5 over n. And then this I is just going to be carried over kind of almost like as a variable. So this x sub I can be simplified to 5 over n I. So this is kind of our pieces that we need in order to kind of get our setup. We're going to do one more thing with this x sub I, but I do want to kind of set up our formula here. So we know that we're evaluating the integral from 0 to 5 of x squared dx. And we know that that's equivalent to the limit as n is approaching infinity of the sum starting at my subinterval of 1 and ending at my subinterval of n of f of x sub I times delta x. So what we know right now is we know our delta x, and we also know our x sub I. We said our x sub I is 5 over n I. But what we also need to know in order to plug in for this part of our formula is what is f of x sub I. So what happens if I plug this x sub I into the function? So what happens if I plug that into my x squared function? So that's going to be kind of our last piece of initial information that we need in order to help us calculate. So I'm going to go ahead and I'm going to calculate what is f of x sub I. So again, my function is x squared. So I'm just going to go ahead and I'm going to replace this 5 over ni into my x over here. So in this case, that really means that I'm going to be squaring everything in here because there's no plus or minus. So I can just go ahead and apply the square to everything. So this is going to be 25 over n squared I squared. So my f of x sub I is going to be 25 over n squared I squared. So then I actually have both the pieces that I need to plug in here. Now I know what f of x sub I is, and I also know what delta x is. So I'm going to carry down my limit as n is approaching infinity. I'm going to carry down my summation here. And then I'm going to go ahead and I'm going to plug in what I know. So my f of x sub I is 25 over n squared I squared. And I'm going to be multiplying that by delta x, which we know is 5 over n. And I'm going to multiply this out. So I just kind of want to simplify things in here before I continue with my solving, or simplification, I should say. So if I multiply in here, 25 times 5 gives me 125. N squared times n gives me an n cubed. And I'm left with this I squared. So at this piece, or at this part, we know that we have a summation here, and we know that we have an I squared. So this is kind of where this piece comes in up here. What we need to be able to do is we need to be able to substitute in one or more of these quantities in for something that I have down in my kind of simplification process here. But we know that we have the summation of c, or the summation of I, or the summation of I squared. Right now I have the summation of 125n cubed over I squared. So what I need to do is I need to kind of isolate this I squared so that I'm able to actually substitute in this quantity. So what I can do is I can actually pull out that 125 over n cubed, and I can pull that out in front of the summation. So I'm going to write my limit as n is approaching infinity, and I'm going to say that's 125 over n cubed. And what we're really doing is we're really taking that summation from I is equal to 1 to n, and now we're left with that of just I squared. So this quantity here is exactly what we have written up here. So what we're going to be able to do is we're actually going to be able to replace that with this n times n plus 1 times 2n plus 1 over 6. So I'm literally going to be taking this quantity and I'm going to be replacing this term with that n times n plus 1 times 2n plus 1 over 6. This limit is still going to stay, and this 125n cubed is still going to stay. I'm just replacing this stuff because that's exactly what I have up here. So my limit as n is approaching infinity of, I'm going to keep the 125 over n cubed, and I'm going to replace this part with n times n plus 1 times 2n plus 1 over 6. And then I want to simplify this as much as possible because eventually we are going to be taking a limit as n is approaching infinity, which we've done before in, I think that was section 2.4 in our book. So what I want to do first is I actually want to simplify the n's if possible, because we know that this is multiplication. I can actually get rid of one of these n's here. So I'm left with just an n squared in the denominator, and I'm getting rid of one of the n's in the numerator. So the limit as n is approaching infinity, I'm left with 125 times n plus 1 times 2n plus 1. And then I'm left with a 6n squared in the denominator. And what I'm going to do is I'm actually going to multiply that out in the numerator as well. Again, just making sure to bring down my limit in each one of my steps. So 125 times 2n squared plus, I think that gives me 3n plus 1 over 6n squared. So I think that gives me, what's that, 250 n squared plus 375n plus 125 all over 6n squared. So what I want to be able to do at this point is I want to be able to actually take the limit as n is approaching infinity of each one of these terms separately. So what I'm going to do is I'm going to actually break these apart into 3 separate fractions, each with a denominator of 6n squared. So 250n squared over its own denominator plus 375n over its own denominator, and then plus 125 over its own denominator. And now I want to simplify as much as I can here. So I'm actually going to go ahead and just kind of simplify if I have any n's that can kind of cancel out. Move up here because I'm kind of running out of room. So this term, my n squares actually go away. So I'm left with 250 over 6. Plus one of my n's can get canceled out here. So I'm left with 375 over 6n. And then nothing cancels here. So I'm just going to leave that as 125 over 6n squared. So remember that when we were taking the limits as x's were approaching infinity, if there was a variable in the denominator, we said that those terms were going to go to 0. So both of these n terms actually go to 0 when we take the limit as n is approaching infinity. And for any constant, remember that we said that limit is just the constant. So I'm going to go ahead and I'm going to take the limit of each one of these terms. So the limit as n is approaching infinity of 250 over 6 is actually just 250 over 6. Limit as n is approaching infinity of this term, since there's an n in the denominator, that's going to be a 0. And then we have an n squared in the denominator here. So if I take the limit as n is approaching infinity here, this would also be 0. So that leaves me with 250 divided by 6, which we can simplify to be 125 over 3, which guess what is 41 2/3, which is exactly what we said the area under the curve was when I had you guys do the investigation of this last week. So what I'm going to do is I'm going to end this video. I'm also going to make another video for the next example because the next one is a little bit more involved than this one, but hopefully this can kind of get you started on this type of problem, and stay tuned for the next video.